An alternating series is a series whose terms are alternately positive and negative. For example, when looking at this series, notice we have negative 1 raised to the n minus 1. That's going to alternate the terms between positive and negative. Let's see what we get. When n is 1, we have negative 1 raised to the 0 times 1 divided by 1. That's just going to give us 1. And then we'll get n is 2. Negative 1 raised to the 1 will make it negative, and then we get 1/2. So think of that as minus 1/2. And then if n is 3, we get 1/3. If n is 4, we get minus 1/4. And you might start to recognize these numbers, but they're alternating. Notice that 1 over n is the harmonic series. So the fractions may look similar to something you've seen in the past. We just have alternating signs this time. So when we have this generic setup of an alternating series, we can use the alternating series test, which means we need to do two things. We need to check to see if the limit at infinity of the sequence is 0. You may remember that from divergence test in the past. And we also need to make sure that the sequence, the terms, are decreasing. So a sub n plus 1 is smaller than the previous a sub n. If those two conditions are true, we have a convergent alternating series. Let's look at a visual to kind of envision what's happening. Let's say we're starting at 0, for example, and we add a sub n. That's going to push us over here to, in the past we called this a partial sum. Let's call it our first sum. And now we're going to subtract, so this was actually addition. Now we're going to subtract a smaller number. So we're subtracting a 2. That's going to push us here and our second partial sum. Then we're going to add again a smaller number. So we're adding a 3. That's going to put us at S3. And we're going to repeat this pattern. Now we're going to subtract a smaller number. So we'll subtract a4. That pushes us at our partial sum 4. And this is just going to continue until essentially S infinity. And we'll converge to a number. That's visually what's happening with a convergent alternating series. Let's look at an example that I briefly mentioned earlier. This is actually the alternating harmonic series. 1 over n is the harmonic series that we're used to, but now we're alternating between positive and negative. Let's test to see if it's convergent or divergent. The alternating series test, first we want to test for divergence. So step 1, let's test for divergence. Very similar to the test that we've done in previous videos. We want to take the limit as n approaches infinity of our sequence, and hopefully it's going to give us 0. So let's see what happens. The limit as n approaches infinity of 1 divided by n. We're going to ignore the alternating part for now and just focus on the 1 divided by n. And we already know that this is going to give us 0. So the first test passes. It's not divergent. Step 2, we want to show that it's decreasing. And there's a couple different ways we can do this. We can use the first derivative test, or we could simply show that a sub n plus 1 is less than or equal to a sub n. So let's do that. A sub n plus 1 is going to be 1 divided by n plus 1. And we know that that is less than or equal to 1 divided by n. If the denominator gets smaller, the fraction gets bigger. And 1 divided by n is a sub n. So we've shown that a sub n plus 1 is less than or equal to a sub n. So it passes this test. It's decreasing. So what we can say now, by the alternating series test, we do have to state which test we're using. We can say that the series from n equals 1 to infinity of negative 1 to the n minus 1 times 1 divided by n is convergent. So that's kind of interesting. We have the alternating harmonic series, which is convergent. But if you think about the harmonic series, just 1 over n, this, we proved in a previous video, is actually divergent. So the regular harmonic series is divergent, alternating harmonic series converges. In our next example, we again want to test for convergence or divergence. Notice that we are alternating between negatives and positives, so we may be able to use the alternating series test. Let's first see if we can write this as a sum. We have the sum, n equals 1 to infinity, and we know it's alternating, so we'll use negative 1 to a power. The question is, what power do we use? Notice that the first term is negative, so if n is 1, we'll get a negative 1, so we'll keep that. We don't want to do n minus 1 or n plus 1. We use those values for the exponent when our first term is positive. And now let's look at the piece beside that. In the numerator, we have 2, 4, 6, 8. Those are even numbers, so we can think of that as 2 times n. And in the denominator, we have 5, 6, 7, 8, 9. It looks like we're adding 1 each time. So if we're starting with n being 1, then we would need a 4 plus n. If n is 1, we would get 5. Then if n is 2, we would get 6. N is 3, we would get 7, and so on. So here we have the series notation. Step 1, test for divergence. To do that, we take the limit as n approaches infinity of the sequence. 2n divided by 4 plus n. Again, we're going to ignore the alternating part for now. Limits at infinity, we divide the numerator and denominator by the highest power of n that occurs in the denominator. We now have the limit as n approaches infinity. The numerator will be 2, and in the denominator we'll get 4 divided by n plus 1. Now we can evaluate the limits. If this denominator is getting big, this fraction is going to 0, which looks like we have 2 divided by 0 plus 1, or 2. Now notice that is not 0. So we took our limit, we did not get 0. That means that this diverges. Remember, if we don't get 0 when we're testing for divergence, we get a divergent series. We don't even need to do step 2 where we test for decreasing because it diverges. So we can say the sum from n equals 1 to infinity of negative 1 to the n times 2n divided by 4 plus n diverges by the test for divergence.